1.3, equations and graphs of polynomial functions. The key concepts in this lesson are the graph of a polynomial function can be sketched using the x-intercepts, the degree of the function, and the sign of the leading coefficient. So we're going to do some curve sketching there. The x-intercepts of a polynomial functions are the roots of the corresponding polynomial equation. So roots are solutions of an equation. X-intercepts equal the zeros equal the roots. So the words are just interchangeable. So that's what we're trying to say here. When a polynomial function is in factored form, the zeros can be easily determined from the factors. When a factor is repeated n times, the corresponding zero has order n. So sometimes we can repeat factors. And the zero of odd order polynomial function, so if it's a n equals 3 or 5, an odd number, changes concavity at the x-intercept. So you're going to see a little change in the curve, right? Zero of even order, like n equals 2 and 4, touches the x-intercept but does not cross the x-axis. So for example, f of x equals x minus 4 times x plus 3 squared times x minus 5 cubed. So the exponent of whatever the factor is indicates its order, okay? And being an order 1, an order 2, an order 3 signifies what that looks like, what that zero looks like on the graph, okay? So for things that are of order 1, you'd have your root at 4 for x minus 4, and the graph will just cross that straight through. Okay. For things of order 2, so x plus 3 squared, you'd have a 0 at -3, right? The graph will touch the 0 and turn around. It's like a turning point. So it is a root still, it's a 0, it's an x-intercept, but it's also a turning point. And for functions of order 3, so x minus 5 cubed, let's say here at 5, okay, we will experience something that looks like this. So curvature, changes in curvature, changes in concavity. Okay, that's what that looks like. So you have something that's curving downward here, right? Sort of curving downward, and then once it hits the 0, the root, it starts to curve upward. Okay. Concavity. If you think of like concave lenses in physics class, right? This is concave downward, concave upward. Where's the concave facing? So it changes concavity, right? So that's still different than saying it goes straight through, like on the first example. This one goes straight through, no change in curvature, right? So that's what you would get of order 3. And we'll mostly deal with these first 3 orders in our class here. Okay. So do not get let's move on. Do not get mixed up between an even power function versus an even function. Okay. Even power versus just an even function. An even power indicates the leading coefficients variable has an even exponent, whereas an even function has a graph that's symmetrical on the y-axis, x equals 0. Okay, so an even power function may be x to the power of 4, but it could have other terms, x cubed plus x squared, okay, plus x. Even functions, yeah, their degree would be even, but every term has to be even, right? You cannot have an x cubed, you cannot have an x. Right? It has to have an even degree for every term. And there's an algebraic definition for even functions as well, which we'll explore just shortly. Okay. And the same concept applies to odd power functions versus odd functions. Okay, so an even function, symmetric about the y-axis, which we have established. Vertical line symmetry at x equals 0. The exponent of each term must all be even, like I just showed you in the last page. And here's the algebraic reasoning. it satisfies a property that f of negative x is equal to f of x for all of its x in its domain. So if I change the input to negative x, the resulting output should still be the same as I had for f of x. Odd functions. These are symmetric about the origin, so there's going to be a point symmetry at 0, 0. The exponent of each term must all be odd. You cannot have any x squareds or x to the power 4th terms in there. And algebraically, it has to satisfy the property that f of negative x equals to the negative times, or negative 1 times f of x. Okay, so for every input of negative x, the output will be negative f of x. Okay, let's look at some examples. Example 1, for each polynomial function, state the degree and sign of the leading coefficient. Describe the end behaviors, determine the x-intercepts, and sketch the graph. Okay, so state for part A, f of x equals 3x times x minus 5 times x plus 4. So now we have something in factored form, not in standard form. Okay, but I can still extract the degree and leading coefficient. So I can expand the factored form into getting the standard form. So f of x, let's move this up a little bit. F of x equals, so again, expand, multiply, 3x squared minus 15x times x plus 4. Expand that further, we get 3x cubed plus 12x squared minus 15x squared minus 60. And then if I simplify, I get 3x cubed minus 3x squared minus 60. Okay. 60x, I forgot the x. There we go. Okay, so we can read this by looking at the highest, the term with the highest exponent. 3 is the leading coefficient. So we have a degree of 3 and a leading coefficient of 3. All right, so that satisfies the first part. The second part, describe the end behaviors. So knowing that this is a function of degree 3 with a positive leading coefficient, that tells us we go from start at quadrant number 3 and at quadrant number 1. Okay, so as x goes to negative infinity, y goes to negative infinity. As x tends to positive infinity, large numbers, y tends to very large numbers, positive infinity as well. So that satisfies number 2. Number 3, determine the x-intercepts. Now, since we do have factored form, we can get the x-intercepts directly from the factored form by setting f of x equal to 0. So 0 equals 3x times x minus 5 times x plus 4. And here you can get this, look at these factors here for 3x. We have x equals 0. When x minus 5 is equal to 0, the only value that satisfies that is 5, so x equals 5. And for x plus 4 to equal 0, the only value that satisfies that is if x equals negative 4. So therefore, your x-intercepts are, if I write them properly here, as coordinates, they are 0, 0, 5 and 0, and negative 4 and 0. And then we sketch. So to sketch my graph, good idea to always have a ruler handy with you. So we're going to draw some axes, and a sketch does not have to be picture perfect accurate. It just has to have all of the correct elements. Okay, and so what we're looking at here is something that starts in quadrant 3 and ends in quadrant 1. It's going to have 3 zeros here at 0, 0, negative 4 and 0, and 5 and 0. Okay, and yeah, good idea to label them too. So negative 4, 0, and 5. All right, and so we can simply draw our sketch. If we start at the bottom of quadrant 3 at negative infinity, we go hit our 0, negative 4. That better. Okay, and then we're going to have a turning point to go back to the other root and turn again to go back to the third root and onward into quadrant 1 to positive infinity. And I'll just draw my arrows to show that the graph continues in both directions. So as you can see, we have 2 turning points, and that corresponds to a function of degree 3, right? N minus 1 turning points. 3 minus 1 is 2. Okay, so yeah, if you need to remind yourselves of that, let's say that degree 3, therefore n minus 1 equals 3 minus 1, which is equal to 2 turning points. All right, there you go. So that was the first example. Let's still go back up and look at the next one. G of x equals 2 times x plus 3 squared times x minus 1 times x minus 5. Now, without expanding the entire polynomial, can we determine the degree and leading coefficient? Right? So if I look at degrees, the exponents of each of these factors, right? 2 plus 1 plus 1. I know if I multiply out the x's, I'm going to have a term with an x term with a degree of 2 plus 1 plus 1, which is 4. I'm going to have an x term of x to the power 4. That's going to happen. So I can simply add the exponents of each of my factors to get that leading, that highest degree. Same thing over here, right? In the first example, I could have taken x to the power of 1, this factor to the power of 1, this factor to the power of 1, add the ones, I get 3, and we know that we have a degree of 3. Same here, you can do that, and we get a degree of 4. Now, the sign of the leading coefficient, well, it's positive, right? So that was part 1, right? The sign of leading coefficient. Well, here's the leading coefficient right here. In absence, assuming that everything else is it's a 1, 1x, 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 eventually your highest degree term will have that leading coefficient of 2. Okay, so your leading coefficient equals 2. It's positive. Oh, sorry, I should make I should correct myself on that. No, actually that's fine. No, it's okay. All right, so number 2, that was part 1, right? Part 1, state the degree and sign of leading coefficient. Part 2, describe the end behavior. So we know it's a even degree function. So that means the end behaviors are going to be either up or down. But because the leading coefficient is positive, the end behaviors are going to be up. As x goes to negative infinity, y is going to go up to positive infinity. As x goes to positive infinity, y is going to go up to positive infinity. Okay. Maybe more formally, I could say g of x instead, right? G of x is positive infinity. All right, let's look at x-intercepts for part 3. Determine the x-intercepts because we have factored form. We can get them from there. So we have x equals, again, let's properly write this as 0. Set g of x equal to 0. So 0 equals 2 times x plus 3 squared times x minus 1 times x minus 5. So for x plus 3 to equal 0, x has to be negative 3. For x minus 1 to be 0, x has to be 1. And for x minus 5 to be 0, x has to be 5. So there are my 3 x-intercepts. I can write those out. Negative 3 and 0, 1 and 0, and 5 and 0. Those are the x-intercepts as coordinates. And then number 4, we have enough now to sketch the graph. Okay. For a function that's let's draw a grid first. So here we have grid. And let's plot some x-intercepts. So negative 3, 1, and 5. Okay, and behaviors are both up positive. So I'm going to start from there and there. Okay, and we've got, well, let's be careful now. Look at the multiplicity. Okay, it's another word I'm using, throwing at you. What we're talking about is the order, right? The order of the factors. So we have something of order 2, or some books will say multiplicity. So multiplicity of 2, which means we have a turning point at that root. So we have a turning point here at -3. But the other ones are fine. The other ones will go straight through. So if I draw my function, I'm going to have a turning point at -3. It's got to turn around somewhere again to come back down to 1. It's going to go straight through 1 because there's only a multiplicity of 1. It's of order 1. It's going to turn around again and pass through 5 until it reaches the first quadrant, positive. So there's a sketch of our function. And we can see here we have 1, 2, 3 turning points, which corresponds to a function of degree 4. So there's our sketch. Okay, let's look at another one. Okay, so h of x equals negative times 2x plus 5 cubed times x minus 4 squared. Okay, so again, look at your exponents as an indication of what is the degree of this function. So if I look at 3 and 2, this is going to be of degree 5. If I add 3 and 2 together, I get 5, which means ultimately, if you expanded all this, all the x's, you're going to have a term with an x to the power 5. Your sign of your leading coefficient, well, there it is, negative, right? And if I, if I think about, okay, 2x times x, 2x cubed, that's positive, positive times negative, it's still going to be a negative leading coefficient. Okay, so your degree for part 1, the degree equals 5, and we have a negative leading coefficient. Okay, part 2. So we have a negative odd degree function. So a negative odd degree means we have something that starts in quadrant number 2. So starts in quadrant number 2, ends at quadrant number 4. So in terms of our end behavior, as x approaches negative infinity, then I should probably use the function notation here. H of x will approach positive infinity if we're in quadrant number 2. And then as x goes to very large positive values, we're going into quadrant 4. So h of x will approach negative infinity. In terms of our x-intercepts here, we are going to look at 2x, so set h of x equal to 0. So 0 equals negative times 2x plus 5 cubed times x minus 4 squared. And solving for x in the first factor, here we have x equals negative 5 over 2. And the second factor, here we have x equals 4. So those are my two x-intercepts. As coordinates, we can write them as x-intercepts, negative 5 over 2 and 0, and 4 and 0. And certainly 5 over 2 might be easy. If you're graphing this on a grid 2.5, negative 2.5, might be easier to understand, to plot. But for now, I'm just going to leave this as a fraction, negative 5 over 2. And so then all that's left really is to sketch the graph, being cognizant of the multiplicity of the factors here, or the order of the factors here. Okay, so let's plot, or let's draw another grid. And I'm going to plot my roots here. So negative 2.5, let's just say negative 5 over 2, and then 4 and 0. All right, so there you go. The end behaviors. So again, we're going to start in quadrant 2, end in quadrant 4, and multiplicity. 2x plus 5 cubed. That means my root is going to look something like this, change in concavity. It's going to be a change in concavity there. And for x equals x minus 4 squared, that's a order 2, so it's going to be a turning point. So it looks something like that. How do I know to draw it below the x-axis, not above the x-axis? Is because I know the end behavior has to end up going down this way. Okay, and then the end behavior on the left side can go approach that, Okay, if I want to be a little bit more exaggerating, I can try to exaggerate the change in concavity a little bit more. There you go. But at some point, this has to have another turning point to come back to the x-axis again. Okay, so there you have it, a degree 5 function. All right, let's look at another example. Well, why don't you pause the video and you try this one on your own. Okay, hopefully you got a chance to try it. So first thing you need to determine is a degree. And so don't forget, there's the invisible 1 for this factor x minus 2. So 2 plus 1 plus 3 equals 6. It's a degree 6 function. The negative leading coefficient here with the negative 3. So that tells us as our end behavior, as we're going to go from quadrant number 3 to quadrant number 4. Okay. X-intercepts are -5, 0, and 2. And don't forget, when you plot your graph, the order or multiplicity of your factors. So at -5, it's of order 3. So we're going to have a little change in concavity from concave up to concave down. At 0, we have an order 2. So it's a turning point at that root there. And then at the other x-intercept at 2, that's order 1. So it's going to go straight through that x-axis until it reaches -infinity for our end behavior. Okay, so that is a little bit of a taste of sketching based on some information, just 3 pieces of information about a function. Let's continue. Number 2, without graphing, determine if the polynomial is even or an odd function or neither, and state if it has a line of symmetry, point symmetry, or neither. So let's look at the first function. -5x to the power 4 plus 3x squared. Okay, so potentially it could be an even function. We have an even degree here. And so let's recall what the even function definition is. Algebraically, it should be if we have f of -x, the result should be the same as f of x. Okay. So what happens if I put in -x? So f of -x equals -5 times -x to the power 4 plus 3 times -x squared minus 4. Well, it turns out -x times -x times -x times -x is positive, right? So -5 times x to the power of 4. -x times -x is also going to be an x squared. So plus 3x squared minus 4. The end. Okay. So what does that say? Therefore, f of -x is equal to, well, if I compare them, yeah, they're exactly the same as f of x. And so this is an even function. And has line symmetry about x equals 0. Right? So again, that's for an even function. And again, this statement tells us whatever y value you have on the left for a given x is the same y value on the right of the y-axis for a given value of x. Okay, so it is an even function. Let's look at the next one. F of x equals x times 2x plus 3 times x minus 2. Okay, so we can see here we have a function of degree 3. It's of odd degree, so we might want to use the other formula, f of -x equals -f of x, to determine if it has point symmetry. Okay. So we'll start with that. F of -x equals, let's replace x with -x. 2x plus 3 is going to be -2x plus 3. And x minus 2 is going to be -x minus 2. Now let's expand and simplify here. So let's say -x times -2x is positive 2x squared minus 3x. And then that's in brackets times -x minus 2. And expand that even further. 2x squared times minus x is minus 2x cubed. And then we have minus 4x squared, and then plus 3x squared, and then plus 6x. If I combine the two like terms, minus 2x cubed and minus x squared plus 6x. All right, so there is f of negative x. What about negative f of x? All right, let's apply a negative. Negative times all of f of x. Okay, so let's expand that. Negative times x times 2x is 2x squared. X times 3 is 3x. Don't forget the x minus 2. Let's expand that. 2x squared times x is 2x cubed. 2x times minus 2 is minus 4x squared. 3x squared, and then minus 6x. And if I combine like terms, 2x cubed minus x squared minus 6x. And if I multiply every term by that negative in front, I'll have minus 2x cubed plus x squared plus 6x. Let's see. Minus 2x cubed minus 2x cubed. Plus 6x plus 6x. But we have a minus x squared and a plus x squared. Uh-oh, not the same. Okay, just because two terms match, one still does not. So we cannot claim that f of negative x equals negative f of x. So therefore, no point symmetry. This is not an odd function, not an odd function. All right. Okay. And how can we tell that? If we looked at f of x, remember how we expanded it over here? If we expanded f of x, there was an x squared term. For an odd function to be an odd function, you cannot have any terms with an even degree, right? So you can have x cubed and you can have x, but you can't have x squared. Okay. So even recognizing that early on, you can go, hey, not an odd function. Let's look at part C. F of x equals 2x cubed times x squared minus 4. Here we have a degree of 5, right? X cubed times x squared, degree of 5, fifth degree, so potentially an odd function. So odd function if f of negative x equals negative f of x, okay? And so let's proceed, right? Let's proceed to do that. F of negative x equals 2 times negative x cubed times negative x squared minus 4. And negative x cubed is still going to be negative, so because it's an odd degree, right? So negative 2x cubed. And negative x times negative x is going to be positive x squared. So it's x squared minus 4, okay? Sure, and then if we do negative f of x, we get multiply the whole f of x by negative 1. So negative 2x cubed times x squared minus 4. So they are equivalent. So we can say, yes, therefore, this is an odd function. All right. Sometimes it might be you might be asked to check for point symmetry. So check for point symmetry. So we're going to substitute 0, 0, because that's the origin point that has to be symmetrical about the origin. And so you would plug in 0 into the function for x, and then you'd get the y value of 0 to verify that the origin is a point on this function. And so you have point symmetry about the origin. Okay, let's look at another example. For each graph, state the x-intercepts, state the intervals where the function is positive and the intervals where the function is negative. Explain where the graph might represent a polynomial function that has zeros of order 2 or of order 3. Okay, so here we have x-intercepts at -3 and 1. Let's use a different color. Okay, and this one looks like it is of order 1, and this 0 here at 1 looks like it is of order 3, because you have the change in, well, order 1 here because it goes straight through, and this one here order 3 because you have the change in concavity. Okay, so where is the graph positive? Where is it negative? So here we're looking at, let's just write the intervals. So positive from negative infinity to -3 in union with 1 to infinity. Okay, and where's the graph negative? Well, it's going to be everywhere else, from -3 to 1. Okay. Looking at the next one, here we have an x-intercept at -5, and that is of order 2 because of the parabolic shape. It is a turning point. And then we have another one here at 3, which is of order 1 because it goes straight through. And then we can talk about where is the graph positive and negative. So positive and negative. Just looking at the y values, we're positive from -infinity to -5. Sorry, even beyond that, all the way to 3 rather. And we're negative from 3 onwards. Okay, and I'm using round brackets for both of these examples because at the roots themselves, you do not have a positive or negative value. This is 0. Okay. Determine the equation for each polynomial function. Here's another interesting one. Okay, so we can start by examining those zeros, right? So we have, where are our zeros? We've got a 0 at -3, which is of order 1. We have a 0 at -1, which is also of order 1. And at 2, which is also of order 1, because they all go straight through the root, the x-intercept. Okay, so what does that tell us? Well, these tell us individually what our roots are. So for -3, if the x-intercept is -3, the root is going to be x plus 3 to the power of 1. For a x-intercept of -1, that factor is going to be x plus 1 to the power of 1. And for 2, we're going to have x minus 2 to the power of 1. And we can use that already to just write down our equation, but we're just missing the leading coefficient. We need a value for the leading coefficient, but I can write down the factors. So x plus 3, x plus 1, and x minus 2. And each of them being of order 1 does not require us really to put the exponent because it's just a 1. Now, when we look at the graph, we can see that, hey, I have my end behavior start at quadrant 2 and goes to quadrant 4. So that tells us that my leading coefficient has to be a negative value if I have this polynomial of degree 3, an odd degree function. So my leading coefficient has to be negative. But I'm not going to play any guessing games here. We're going to use a point and solve for the leading coefficient. So what point are we given? We're given 0 and 8. So use the indicated point. So when y equals 8, x equals 0. So y equals 8. 8 equals a times 0 plus 3 times 0 plus 1 times 0 minus 2. Okay, so that's going to be a times 3 times 1 times minus 2, which is minus 6. So a equals 8 over minus 6, which I can reduce to lowest terms, -4 over 3. So there's my value of a. And so therefore, I can conclude the function f of x is equal to -4 over 3. times x plus 3 times x plus 1 times x minus 2. You can always take, let's say, Desmos graphing calculator and plot that and verify that your answer is correct. Okay. But yeah, it starts from the idea that you take this factored form. You cannot forget the a. You need an a, right? And then you solve for a. Look, another one. So here I only have 2 zeros. I have a 0 at -2, and it has an of order 3 because we can see a change in concavity, right? It curves downward and it curves upward. Okay, so change in concavity, boom, order 3. And then I have another, and that tells us that our factor here is x plus 2 to the exponent 3. And the other 0 is here at 1. Okay, and that has an order of 2 because it's a turning point. Okay, and so that tells me that my factor here is x minus 1 to the power of 2. Okay, so the function for this polynomial, assuming it's a polynomial, right, is going to be in factored form, some leading coefficient a we don't know yet, and then my factors are x plus 2 cubed times x minus 1 squared. And I can use a given point. So they gave us this point right here at 0 and 4. And I can use that given point to help me find the value for a. So f of 0 equals 4. So 4 equals a times 0 plus 2 cubed times 0 minus 1 squared. And so we have a times 2 cubed and 1 squared. So it's going to be 8. 2 cubed is 8. Minus 1 squared is just minus 1 times minus 1, which is 1. And so a equals the 4 divided by 8, which is 1/2. So my function f of x equals 1/2 times x plus 2 cubed times x minus 1 squared. Okay, let's move away from a little bit of the graphs and let's look at description. Determine an equation for the quintic polynomial function. Let's just say quintic. Quintic. We have linear, quadratic, cubic, quartic, and quintic. Okay. So quintic means degree 5. So we're told the zeros are -1 and 3. So order 3 and order 2. So we're told to order 3 and 2. 3 plus 2 is 5. So that verifies that. Passes through the point -2 and 50. Okay. So I can say here f of x equals, if one of the zeros is -1, then one of my factors has to be x plus 1. Order 3 means the exponent is 3. I'll put my leading coefficient there, a. And the other x-intercept, or the other 0 is 3, which means the factor is going to be x minus 3. And we're told that is of order 2. So my exponent here will be 2. Okay. And then I solve for a. If the y value is 50 when x is 2, then I can plug in x equals -2. Right? Just like that. So a times -2 plus 1 is -1. So -1 cubed. -2 minus 3 is -5. So -5 squared. Watch out for the negatives. -1 times -1 times -1 is still a negative. So I still have an a. -5 squared is -5 times -5 is +25. So -25a equals 50. And if I divide both sides by -25, I get a equals -2. So there's my leading coefficient. So therefore, f of x equals -2 times x plus 1 cubed times x minus 3 squared. And using what we already know about all of these things with the roots, the multiplicity, the end behaviors, and all that, we can sketch our graph. Let's start with the roots. We have a root at -1 and we have one at +3. Let's go further out. Okay. And we know the end behavior. This is a quintic, a degree 5 odd degree function with what? A negative leading coefficient. So we know we're going to start at quadrant 2 and we're going to end at quadrant 4. Okay. The root at -1 is a multiplicity of 3, so it's going to change concavity like that. And the root at 3 is quadratic. It's a turning point. It's going to go like that. I know I have to end up this way. I know we're going to end up this way. And so somewhere here, I have to have another turning point. There's our sketch. Again, I'm not expecting, or I don't think, well, if you were taking the class in person with me, I would not be expecting perfect, picture perfect Picasso like a graph, as long as the important elements are there. All right, so that ends this lesson. Have a look at some of the practice problems in the textbook, and I will see you in the next video.